My name is Simone Esposito. For those of you there, I will be the chair of this second session of the workshop. So the first speaker today for this session is Charlotte Bond and co-workers presenting a talk about pyramid wavefront sensor challenges in the ELT era, HARMONI, SCAO perspective. I just remind the speaker you have about 15 minutes and questions can be done on the different chats that are available. Please, Charlotte, you can start.
Hey, hope everyone can hear me. So yes, today I'm going to be talking to you about some of the challenges we've encountered in our design work for the HARMONI SCAO system. Okay, so firstly, just a little overview of what HARMONI is. So HARMONI is a near-infrared and visible integral field spectrograph for the European ELT. There are 3 modes of operation, but today I will be focusing on the SCAO mode. So the baseline for HARMONI SCAO is a visible pyramid wavefront sensor with 100 pixels across the pupil, nominally a frame rate of 500 Hertz and a modulation of 3 lambda/d. So with this visible wavefront sensor, we'll be then controlling around 4,000 modes, and that will be controlled through the M4, so the ELT deformable mirror. And as well as this sort of main AO loop, we also have a lower order loop, which is part of the HARMONI instrument and is designed for NCPA correction, so that we can operate with a flat wavefront on the pyramid whilst optimizing for the science. And so the ELT of course provides us with the higher order wavefront control through M4, which is a segmented DM with 6 petals. We then have the ELT pupil, which looks like this. And so I just wanted to point out here the spiders here, which have caused us which have been challenging for us to deal with on the wavefront sensor side. So these are around 50 centimeters wide, which means they're wider than a single pixel on the pyramid wavefront sensor. So our single pixel is 37 centimeters. And these segments match the DM segments. So one of the key challenges for us is controlling what we call the petal modes. So that fragmentation of the pupil by the spiders leads to some modes which are very badly seen by our wavefront sensor. So this sort of segment piston modes, or petal modes as we call them. And because they're badly seen, they can propagate in the AO loop, and we can end up with very large wavefront errors, basically where the loop stabilizes with kind of multiple waves of these modes. And this seems to be particularly challenging at smaller wavelengths, so for example in the visible. So here's an example of if we just close the loop without doing anything to mitigate this effect, we get thousands of nanometers RMS in wavefront error, and the PSF starts to fragment. So our baseline solution for dealing with this effect is something we call edge actuator coupling. So basically we pair actuators across the spider, across the segment. So we do this in the control space, and then they act as a single actuator. So you would have an influence function, something like this. And this basically limits the DM's ability to create those sharp discontinuities. So let's have a look at the baseline behavior. So here you have a plot of the residual and the turbulent wavefront RMS. And so this is using this edge actuator coupling approach. So you can see that we avoid those large petal errors. So we don't have those large petal modes developing. We have some good stability. and around 125 nanometers RMS residual at our median seeing conditions. But you can see that there are some spikes in the residual. So these really correspond to flare-ups in the petal modes that you can see here. So you can see where there's no spikes, the amplitude of those petal modes is much lower. And so we can recover when they flare up, but we would like to see if we could improve on this control of the petal modes. So one key thing for our edge actuator coupling approach, to optimize that performance, we really needed to consider exactly the influence functions we're coupling across the edge. And what we found was that we needed to to include a sort of coupling factor rather than use the as is ESO influence functions. So these are the ESO influence functions, and what we do is we do a linear sum of them to create something that's slightly more Gaussian. And here you can just see the kind of average performance versus that coupling factor. So we typically use a value of around 40%. If you do something too large, you eventually are able to create these sharp discontinuities again, and we create a lot of petal modes. Modulation is, of course, a key parameter. And actually, a smaller modulation does improve our sensitivity to the petal modes. So here you can see this is the residual, and the red trace is for 3 lambda over D, and the yellow is for 2 lambda over D. So you can see that with the red trace is the 2 lambda over D. So you can see with a lower modulation, the kind of amplitude of these flare-ups of the petal modes is smaller. And you can see here, this is a plot of the kind of average residual wavefront versus modulation. So we could reduce the modulation a little and improve our performance to the petal modes. Unfortunately, of course, there are other things that we need to balance against, and we do find we become unstable if we go to too small a modulation, even with sort of optical gain compensation. So we may want to stick with 3 lambda over D to avoid getting too close to that region of instability. So talking of optical gains, our baseline approach to deal with optical gains in HARMONI is to basically use an estimation of the fitting error in a convolutional model to estimate the optical gains for each mode. Then that is compensated on the command matrix. And so you can see here a plot of seeing versus the performance with and without this optical gain compensation. One thing we wanted to look at was if we could basically adapt the optical gain compensation approach to improve the control of the petal modes. But really what we found was that using a single value per petal mode was not enough. So that's shown here in the kind of the yellow trace. So this is basically estimating the optical gain on the petal modes using that convolutional approach, and then applying that. But what we find is that there is a lot of cross-coupling between the petal modes. So actually what you need is the red trace is basically taking an on-SCAO command matrix of the petal modes. But in this case, it's something unrealistic because I do it at every iteration. So that was just to kind of investigate and see exactly what was, how this behavior manifests itself. Another aspect we've been looking at is exactly how we want to process our wavefront sensor signals. So there's 2 different things we considered: the classical slopes approach, and then the pseudo intensities. So basically you take the intensities, you normalize them, and you remove a reference. So there are plus and minuses to both approaches. The slopes are smaller in size, so you have half the amount of data, so you have less computations to consider. However, the pseudo intensities do have smaller requirements, or in fact, they don't have really requirements on the position of the pupil images. Whereas the slopes, because you're combining those different pupil images, they do require some tight tolerancing on the pupil positions or some oversampling. Otherwise, you're going to smear out information at high spatial frequencies. And we did some tests of this. So this is a simulation showing, so I'm shifting each of the pupil images in X and Y. Up to 1/4 of a pixel, so that would correspond to half a pixel separation of the pupil images. And you can see that for the slopes, we start, the performance starts to degrade. Eventually it becomes unstable, but this is really concentrated at the pupil edge, and I think with some regularization, we'd be able to avoid the instabilities. But you can still see that the performance does degrade unless you have, compared to the pseudo intensities, unless you have an integer number of pixels separating the pupil images. And actually what you see here is exactly what Carlos was talking about, the kind of super resolution effect that you have when you have the pupils shifted with respect to each other, and you use the pseudo intensity method. So just to have a look at well as the contrast as well as the overall residual. So on the top we have the residual PSD of the slopes and then the pseudo intensities. And then here we have the ratio of the two, so the kind of relative contrast improvement. So this is ignoring the cases where it went unstable. So you can see you get an improved dark region using the pseudo intensities and sort of improved contrast almost up to a factor of 3 for high spatial frequencies. And so this kind of is basically showing us that we lose some information with the slopes map if we don't have a non-integer separation of the pupil images. There's potential for super resolution using the intensities if we have a non-integer separation. And so in our case, the RTC constraints allow us to use the intensities, so that is now going to be our baseline. And just obviously Carlos already gave his talk, but Jean-François also discussed this effect as well. Okay, and finally, just to point out that this baseline solution works well with turbulence, but our initial tests, if we have some M4 phasing errors, show that we can't really recover the phasing. So, I mean, the good news is that all the other modes are well corrected, but we can't phase it just with the pyramid wavefront sensor as the baseline configuration is now. Jean-François and Nicolas will talk more about those and potential ways we're going to look at dealing with those sorts of phasing errors. So just a quick conclusion. So we're using the edge actuator coupling method to avoid buildup of petal modes. So that's our baseline. We've investigated various elements, and we're now going to move ahead to use pseudo intensities over slopes. And now we're really needing to look at other approaches to contend with phasing errors and to hopefully improve on our control of the petal modes. So maybe more looking at super resolution, some spatial filtering perhaps, and finally some second stage petal measurements. Thank you.
Okay, Okay, thank you, Charlotte, for the presentation. I see here a question arrived right now from Silvano Berti. I can read it to you. If I understood well, you have shown that the non-SCAO CM was more immune to petaling. How about using a synthetic CM but computed with a PSF residual wavefront that is more representative of the nominal working regime than a diffraction limited PSF in air band? That's the question I got from.
So maybe I can just go back to yeah. So basically, yeah, I guess so. It's basically what this is showing is that it's more complicated than using a single value and using and basically doing a kind of scaling of each optical mode. So I think we would have to need quite a lot of information about the exact shape of the PSF and maybe about the contribution of the other petal modes, because there seems to be quite a lot of cross coupling between the petal modes. But yeah, I mean, yeah, I didn't look much further than this. It was just to show that the kind of optical gain approach is trickier to apply in the case of the petal modes.
Yes, I think it was a good answer. We have a second question from Jean-Pierre Veran. Charlotte, they say, in your graph where you show the performance collapses when you compute slopes if the shift is larger than 0.25 subaperture. This is computed with a free geometry, right? For an oversampled pyramid wavefront sensor, yes, exactly this one, it should not collapse, right?
So it's I haven't tried it with the free geometry. So we have the geometry of M4, which is a hexagonal geometry. And if you're, I mean, I think it's still true if it would depend on the sampling, the oversampling factor that you have compared to the highest spatial frequencies that you're controlling. I mean, what we find is if we reduce the number of modes we control, we don't get this instability. So it really is the ratio between your oversampling and your highest spatial frequency.
See, yes, here I think Jean-Pierre is correct. The oversampling are less sensitive to this error. Of course, you show here that in this case, a differential 0.2 in this radial shift comes out as a 0.5 displacement of a subaperture for the, say, standard classical signal computation, and then it's it can be too much for a.
So yeah, so this is the shift of an individual image, but the relative shift, say between P1 and P2, like in the X direction, is half.
It's twice.
Yeah. And it's just showing that in the slopes, when they're perfectly aligned, the slopes and the pseudo intensities have exactly the same amount of information, but when the pupils are shifted, there's some information that's lost when you go to the slopes, and you are sort of smearing the higher spatial frequencies together. So, I mean, you can either require higher tolerances, or you can oversample more, or you can use the pseudo intensity. But I think this instability would be, you could do some regularization and avoid that instability as well.
Yeah. Okay. I think there are no more questions for you, Charlotte. So we thanks again for your presentation. And if you unshare the screen, we go on with the next one. That is final development of a high-speed visible pyramid wavefront sensor for the MMT AO system, given by Narsireddy Anugu. Narsireddy, if you're ready to go, you can go.
Can you hear me? Can you see my slide?
Yes, everything fine.
Thank you. I'm Narsireddy Anugu. I'm a staff scientist at RRA. Before I was postdoc at the University of Arizona. Yeah, I'm going to present the status of our visible wavefront sensor developed for the MMT as part of the MAPS project. Jacob already gave you some introduction about the MAPS project. Yeah, this is on this wavefront sensor laptop system. We are collaborating with Toronto team led by Suresh Sivanandam. MAPS is basically upgrade of the refurbishment of the old our legacy opto-optic system, which was stopped working a few years ago. And so this system is funded to upgrade the AO system, including the adaptive secondary mirror, electronics and software, and also science cameras, Aries and polarimeter camera. So this system is aimed at characterizing exoplanet systems using high spectral resolution and polarization camera using high adaptive optics correction system. Yeah, there was a question about the status of the ASM, and yeah, I want to say that it is going well. In fact, one of the requirement for the NSF funding to go next level was to show them the performance. I think they are happy, and they let us go for the next step with approved funding this summer. So the idea is that the new ASM system is optimized for low power emission and higher modes of correction. Before it was using a shock harmonic wavefront sensor with low number of correction. So we wanted to go for higher order correction. So this is the ASM in the lab that was under test using a test source, and if I want to give you a number, it was the actuators are the peak to valley around actually below 10 nanometers each actuator. So they so our expectation is that we go better performance than previous system. A legacy system in K-band was able to deliver around 25% of Strel ratio. The new system, we are expecting that it can go around 75% by making better correction in terms of time, also more number of modes correction. So for that, we also needed better wavefront sensor system. So this is the optical layout of the wavefront sensor. A F15 beams comes from the telescope, and that is imaged by input triplet lens on the a pyramid wavefront sensor, a pyramid for pyramid. Yeah, so pyramid. There are two pyramids, infrared pyramid and visible. So I'm going to highlight about visible part. I think Jacob already covered on the infrared part. This is the mechanical design. So here is the tip tilt modulation system to increase the sensitivity of the pyramid wavefront sensor and dynamic range. And this is the wavefront sensor camera detector, a courtesy of Air Force Lab CCID 75. And other one is this is the infrared wavefront sensor. It uses Saphira detector. So this is the optical design of the pyramid was taken from LBT, which was working well. This is optimized for our specifications, and the visible. This is the pyramid which is built by WZW Optics from Switzerland, and it was delivered last month. Or like 2 months ago. So these are the specifications in a nutshell. We have 30 pixel pupil diameter, and the pupil separation is it's 39 was the design. Now it made it to 40 so that we can use the binning. And the field of view is torque second. We do the design allows 10 lambda by d modulation correction. So we use 80 by 80 pixel window without binning. That is the only one we have on this detector, and we can we plan to use the particular readout region. So this is the wavefront sensor detector. The quantum efficiency is around 80, and it has several readout modes that can be used for binning or operation of the faint stars and bright stars when we can do a binning. This is a acquisition camera, which is nothing fancy, but this allows us to acquire the star on the wavefront sensor cameras. We characterize the camera and modulation system to check their performances. Simple setup just to test their individual performance, and they meet our specifications. CCI ID75 camera gives below 3 electrons readout nice. So that is within our specifications. And there are some numbers that read out nice for different modes. These are old, but we improved on that based by correcting so there is a electrical connections which improve the system bias signal. So yeah, the readout nice are around 3 electrons per different modes. And this is the tip tilt modulator. We use a piezo actuator. It has strain gauges to measure the position, and so this is the performance. This is the frequency response. We require 1500 microradians around to do the 10 lambda by d modulation, but we can do around 3000 microradians. So which is actually we are 2 times above the requirements. So we can do the modulation of 1 kilohertz at 1 kilohertz 10 lambda by d easily. So software, we use 2 computers. One is for the wavefront sensor, and another one is for the ASM control. This is already well written, and it is working since a year. And it's basically, this one runs at 1 kilohertz. speed. And then this waits for the slopes computation based on the visible wavefront sensor or IR wavefront sensor. The idea is one runs at a time. So based on the science target, if it is redder IR wavefront sensor, it's if it's brighter and visible, we use a visible wavefront sensor. Then so if the slopes are ready, it takes the slopes and reconstructs and the wavefront profile or the interaction matrix, control matrix, and then place the correction. And there is another computer for the low latency actuators and also for operational GUIs. So I want to summarize that our current status is the ASM is doing well, and all the optics are so design of the optics is frozen, and mechanical design also almost frozen. So most of the at least the few parts are delivered, and few parts are currently in procurement. Yeah, we were delayed with COVID, and also there was some funding. Yeah, NSF want to see our performance, but there was a delay. So those are the things which delay. But I think the system is in track. Probably it can go next year to the sky. Yeah, I will take any questions if you have.
Okay. Thank you, Nasireddi. For the moment, I don't see a question, but of course, Esteban, let me know if I'm missing anything. I may have just a quick question for you, because I was curious. So you wrote here, the pyramid you received from WZW, they're beautiful, they meet most of the specs. So which specs they did not fulfill? Yeah.
Yeah, this one is so yeah, the software engineer only is measuring that. I think I did not. I don't want to say anything wrong, but the two surfaces which are the front and back surface, when they are glued, there was something wrong, but I don't know what is wrong. But he said that most of the specs are meeting. I think
you're planning to go on sky with these pyramids anyhow.
Yeah. So yeah, this is the there was also, I think it's almost it took 1 year more to deliver the visible part of the pyramid, and IR pyramid they delivered I think quickly, but they took a lot of time to do the visible part.
Okay. So there is a last question, but I think we're a little bit late. Let's say there is a question from Glenn Herriot that says, have you investigated what is the expected lifetime of the piezo modulator at this high stroke and high frequency?
So you mean like if they
the 10 lambda over d and then 1 kilohertz,
it changes within 1 day, or like a so I repeated the experiment frequency, the response thing, like a few times separated by like a months, and it gets the same number.
Yeah, I would say I could give you my comments on this, for Glenn. So at LBT, the pyramid we have there does similar things, because we need 10 lambda over d for basically setup of the system, so for initial bootstrap of the system, and then we have more or less your requirements. And it's now more than 10 years. that those units are working, maybe not every night, but for 10 years long. So I think you can trust that they will resist for quite a few years, I'd say, from our experience there.
Yeah, thank you. I think we did not we don't know for this system, right? Yeah, we have to experience. So yeah, when you operate 10 lambda by D, I think every night, I think it should have a lifetime, but I don't know how many years.
Yeah, if you look at the lifetime, it's 1 billion of operation, but it is not exactly there. So I would say that experience seems to show that these piezos, they can work for quite a long period of time. We're talking of years, I would say. Okay, so there are no more questions. Thanks you again, and I would go to the next talk of the session. The next talk here is first closed loop test of segment piston with a pyramid sensor on the new GMT HCAT test bed, and is given by Laird Close. Laird, you can start.
All right. Okay. Thanks, Simone. So I'd like to talk to you a little bit about a test bed that's been built at the University of Arizona, part of the Center for Adaptive Optics, Astronomical Adaptive Optics, and it's a collaboration with the GMT. And I want to highlight in particular my co-authors, Alex Hegelin and Maggie Kautz, who are optical sciences graduate students, Jared Males, the PI of MEG AOX, and in particular our Sagan postdoc, Sebastian Haffert, who's been helping us with our control, as well as project manager Victor Gasho and Rick Beamers and Anton Boucher, who are helping us from the GMT. So Charlotte Bond already talked nicely about the issue of piston errors, phasing errors when it comes to all the giant telescopes. They can be pedal nodes, or in the case of the GMT, individual segments. And obviously, if you go from a phased telescope, you have a nice PSF, but when you're unphased, the PSF is no longer diffraction limited. Even though the wavefronts across each of the segments are flat, it's not a phased telescope, and therefore it's doesn't produce a diffraction limited image, and so most of the science is lost. So this is a big challenge for everybody on this conference, because all the next generation telescopes are going to struggle with this problem. And the GMT also, of course, suffers from this. We have these large gaps between our individual segments, and the secondary mirror itself is also segmented. So, it's a doubly segmented design. As most of you probably know, the power when you're using a piston mode, if you piston this segment, simulations show that most of the signal fall actually in the gap between the individual segments on the pyramid wavefront sensor. So I'm going to call these things gap pixels. And these gap pixels are very, very important, because as you increase the modulation to increase the linearity of the pyramid sensor, most of the signal, almost all the signal, is in these gap pixels. So it's a kind of a rare case. Even though it's sort of like a low order mode, it looks very high order to the piston sensor, and you're relying on just a few pixels for most of your signal. And so that puts us into an interesting place with wavefront sensing. So for a bunch of reasons, this is actually not trivial, as I think Charlotte was fairly convincing to get working even in the computer. And that suggests that it's complicated. Optical gain calibrations have to be perfect. You have a lot of nonlinear cross coupling. So all of this suggests it's a good idea to build a test bed to actually test these things out in reality. And in fact, the US Decadal Survey called out the GMT and TMT as high priority, top priorities for ground-based astronomy, but pointed out for the GMT, although I argue this is also an issue for the TMT, is that phasing will be is the tallest technical risk. So phasing for the GMT is going to be very, very important. And so here, let's talk about a very simple test bed experiment that we can do. We can take a working AO system, MEG AOX, PIs, Jared males. And so when MEG AOX is not at the 6.5 meter Clay telescope in Chile, we can use it in the laboratory, and we can fool it into thinking it is at the GMT, and we can do phasing experiments with a real pyramid wavefront sensor with a segmented pupil. And we can learn about all the realities of what it really is like to do segment phase sensing, piston sensing with a real pyramid with real optics and real AO hardware. All right, this is a sketch of MEG AOX, the existing instrument. And the highlight is that it's got a 2K DM, 2040 actuator, 2000 actuator deformable mirror, which we can then use for these experiments. And just to show you that it really is an AO system, here it is in Chile, closing on pi pup, and you can see when the loop is closed, we go from seeing limited blob to actually seeing the companion pi pup B. This is just demonstrating that we have a fully working pyramid wavefront sensor, in this case using the pseudo intensities for the closed loop because the slopes are a bit finicky. And you can see our closed loop modulated, we're modulating by 3 lambda over D on the pyramid tip here. All right, so, but of course we want to introduce segment phase. And the quickest way to do that is to just introduce segment phase on one of the apertures on the GMT. That was we wanted this test bed to be up and running quickly. And so our design was basically to reimage one of the GMT segments onto a piezo 325. The 325 piezo allows you to tip, tilt, and piston this segment. So we can pretend that one of the segments on the GMT is moving around in piston and tip tilt. And we can see how well the pyramid sensor can control and sense that. So this is basically, we're taking a section of the GMT pupil, 4 of them, and we're doing tip, tilt, and piston on this particular segment. This will be the experiment that will feed into MEG AOX, and it will close the loop with its pyramid. Here you can see the sketch of the design from Alex, and this is actually the as-built test bed. As you can see it, just actually 2 months after we signed the contract, we had the working test bed up and running. This is the lower table of MEG AOX that I'm showing here, which you can see pretty clearly. Maybe make this into something a little there. Here you can see the lower part of the MEG AOX instrument. This is the chronographic instrument. The pyramid wavefront sensors right here. These are the different science cameras that we use for the various experiments here. We're just closing the loop here. For example, we can run atmospheric turbulence over the tweeter and close the loop. I don't have time to show you the movie because I just don't have enough time in this talk. Here we do our first experiment. Charlotte actually mentioned that as you decrease the modulation, you become much more sensitive to piston errors, but you also become much more non-linear, and so it's harder to actually control with turbulence. So these first experiments I'm showing you are with no turbulence. So we're going to use the piston, we're going to use the pyramid wavefront sensor to sense segment piston, and this is the 0 modulation. So we're not modulating on the tip of the pyramid. We can basically apply a piston error and then see if the pyramid wavefront sensor can sense that piston error and then correct it. So we actually are going to sort of follow a ramp here. The blue dots are going to show its corrected position recovering from that piston error. And as you can see, we just keep adding in piston errors, and the blue line is nice and flat as you'd expect. So that's good. We're sensing piston. We're taking out the piston error nicely. But once we actually get to an error that's greater than half a wavelength, then the sensor actually flips by 2 pi because cos theta is the same as cos theta plus 2 pi mathematically. The wavefront sensor is more or less working at an average wavelength of 850 nanometers, and therefore it can't really differentiate between whether I want to be up here or down here. This is the classic 2 pi wrapping of a wavefront sensor, and we certainly see that with the pyramid sensor as predicted. And here we actually only took a small step, but it actually jumped by 2 pi because it becomes a little bit unstable with large piston errors. And this is sort of, and so on is its behavior. This is pretty much what you'd exactly expect from an unmodulated pyramid sensor. We were happy with that performance. We increased the linearity of the sensor by increasing the modulation to 3 lambda over D of the pyramid sensor. And with those tests, you can see here, we used Sebastian Haffert's software code to do these tests. And Sebastian's code was able to recover that the flatness of these steps when we were modulating by 2 lambda over D was on the order of 13 nanometers, 3 lambda over D was on the order of 33 nanometers. We were even actually able to get 5 lambda over D modulations to work as well. So without turbulence, the pyramid wavefront sensor worked quite well. However, when we actually imposed turbulence with the tweeter by running a turbulent phase screen over the tweeter, we noticed the behavior of the wavefront sensor was much more difficult to control. It would be stable for a small amount of time and then would start to run away and wrap by 2 pi. And here you can see it. We did several different experiments in low turbulence. Here's another low turbulence experiment, and you can see it's starting to run away. One of the reasons we felt that even in low turbulence, we were having trouble closing the loop is charge diffusion on the CCD itself. We're using an OCAM2 unbin 240 by 240. And of course, CCDs don't really have pixels. There's no such thing as a pixel to a CCD. It's a slab of silicon. And of course, the photoelectrons themselves will diffuse through the slab of silicon. And so you always get a little bit of crosstalk between the individual pixels. And this sort of manifests itself as a pixel response function. The problem here is that we're really trying to rely on these gap pixels, the pixels between the segments for the majority of the pyramid signal. And these are confused by the fact that you've got bright light here, bright light here. Light will then propagate into these gap pixels and will lead to fake pyramid piston-like signals to the pyramid sensor. So this is something I just wanted to call out as something you build test beds to find these things out. Of course, it's sort of obvious in retrospect that if you only have 1 or 2 pixels in your gap, you're going to be contaminated by high order terms that are partially corrected by your AO system lighting up those particular patches and making it a bit confusing. Here are more simulations done with the, simulations tests with the test bed in median seeing conditions, 0.64 arc seconds, and the worse than median. And again, you can see the same problem is that we close the loop, but it would quickly run away no matter how many different times and attempts that we did it with different modulations and different gains. So we were sort of struggling here. This is actually kind of similar performance to what Ariel Boutreau-Canto's paper that's been recently coming out in ANA. And she sees similar problems with ELT pedal control. And I don't really have time to go into all of this, but basically what the takeaway from the pyramid sensing part is that CCD charge diffusion coupled with the non-linear cross-coupling makes it very hard to close the loop and control segment piston with a pyramid wavefront sensor in the face of turbulence. However, we need to, of course, fix this problem if we're going to have a working ELTs. And so Sebastian Heffert has been leading an effort to build a different type of phase sensor that just works on sensing piston. So a special piston sensor or a pedalometer, if you will. And the initial idea that I came up with was we would interfere different parts of the GMT pupil and create dispersed fringes from, you just basically interfere the PSF from this patch of pupil with this patch, which gives you basically like a Young's double slit PSF, and then you disperse it from blue to red, and you can actually see individual fringes. This doesn't suffer from the 2 pi phase wrapping problem and gives you a nice linear way of detecting phase. So what this actually...
Leo, you have about 2 minutes nominally, yeah?
Yes, I'm just finishing up. Thanks, Simone. So basically the way this works is you just put in phase ramps into your pupil plane, and you can then, with a liquid crystal that has a resin, and with that liquid crystal, you then can basically interfere whichever pupils you want with each other. So this segment interferes with this segment, which produces this nice barber pole dispersed fringe here. This is what the actual device looks like as built by the test bed. Here's our a micrograph of the actual device as built by Beamco. Here it is inserted into our pupil wheel of MEG AOX. We will use this camera to look at the fringes and this camera to look at the science BSF. And so that's what this experiment looks like. Now the pyramid wavefront sensor just does slopes, does not do piston, and the holographic dispersed fringe sensor, the HDFS, does all the piston. That's what it looks like in the pupil. That's what it looks like actually running. And so here we can have 10 microns of optical path difference between the segments. And you can see this nice barber pole pattern, which can be easily linearly seen by the pyramid sensor, seen by the HDFS signal, and removed. And we're very happy with that. So tomorrow at 1 p.m. Chile time, Sebastian's going to give a complete talk focusing on how well the HDFS works with turbulence. So I'm just going to summarize here. And really the takeaway from this is the pyramid wavefront sensor struggles with sensing piston in the segment piston in the presence of turbulence, but it can be tremendously aided with a holographic dispersed fringe sensor. And together they can work as a very powerful wavefront sensing architecture for ELT size telescopes. All right, there. That's it.
Thank you, Laird. Thanks. And of course, a lot of work we see from this talk. We have a time for a quick question. I think I'll read it, Laird. You have a question from Jean-Pierre Verin. Can you comment on how these phasing techniques could work in the GMT case where the segments are only separated by 2.5 millimeters? Quick answer for
yeah. Okay. Well, of course, I haven't really studied the. Okay, yeah. So let me be clear here. What I'm really talking about are petals more than when I say so. GMT has these big segments, and so in GMT speak we talk about segments, but they're really much more. They would translate to petals for the TMT and the ELT. So it's more of a pedaling. So really what I'm not addressing the individual hexagonal segments of the TMT or the ELT where the gaps are really, really small. Those gaps I'm thinking are small enough that you can use edge sensors to control the piston issues there. But for the pedal modes that Charlotte was talking about, everything that I'm saying is actually applicable. I hope that maybe makes it clearer.
Okay, I think so, Laird. So actually, we have another question, but you may have a look on the question and answer log, Laird, because I think we need to move on. We are a bit late.
Sure. And actually, I think the answer to that question is just see Sebastian's talk tomorrow at 1 p.m. and he'll be able to do a much better job of describing it. Oh, and the very last question by Marcus, in the presence of turbulence, yes, it was, yes, we injected a phase screen and corrected the phase screen with the pyramid, but of course we only corrected 500 modes. And so there was going to be a residual. We only did the first 500 Fourier modes. All right.
Okay. Okay, thank you, Laird. So we'll go with the next talk here. That is wavefront reconstruction and closed loop performance of the METIS SCAO system. Talk is given by Marcus Feld. Marcus, go ahead. You're right. You're go. Do
you have the slides on your screens?
Yeah, we see the slide.
Okay, great. Yeah, welcome everyone. It's a pleasure to be able to talk to you today about the METIS SCAO simulation setup and performance. So I'm Marcus, of course, presenting this. And most of the results shown today were derived by work from Carlos Correa, who is doing the bulk of the simulations, Horst Steuer, who is our software captain. And then from Linz, we have Andy Obereder and Julia Schatokina, and here at MPIA also Thomas Bertram and Stefan Hippler, who give advice from behind, so to speak. So I'm going to show you briefly the design of our system, introduce you to the setup of our simulation system, explain to you a little bit our wavefront control strategy, how we're doing it at the moment, and then show you some examples. And we'll also focus a bit on the paddling problem, which of course is a problem for everyone here. And in the end, the performance, I'll just put up the error budget and show you that it's actually comparable to what we have already seen from others. So here's the layout of our system. It's a pyramid wavefront sensor. With regard to the already heavily discussed paddling problem, we have a slight advantage. We are operating in the near infrared, so our wavelength is longer, H-band and K-band. And we have also a number of peculiarities. That is, we have in the common path in front of the wavefront sensor the field derotator of the instrument and a lateral pupil stabilization mirror, which means that we have to derotate the AO signals in software. And there is a dedicated NCPA compensation mechanism running on the science camera and providing us with updates on NCPA and tilt offsets. So here is the simulation setup. You can see it's pretty complete for now. So most of the things in the top two boxes, blue and red, are implemented in the Compass AO simulation system. We have essentially everything: the signal, the disturbance, which is atmospheric but can also be static, and we can deliberately introduce pedal piston here. We have wind-induced tip tilt, so lots of possibilities to make results bad. The pupil, we have a full M4 model from ESO. We have implemented M4 and M5 dynamics, all kinds of detrimental effects. And we do also of course, everything that the RTC is doing is mainly in Compass modules here. And we have recently also achieved to implement what ESO calls the CCS, that is the control system, which is actually part of the ELT, and will do also will interfere somehow with the actual control. And then there is the soft RTC, which is busy with the derotation that I already mentioned, and a number of other things, NCPA updates, differential tip tilt, and so on. And then we have a set of evaluation modules, which include Compass internal diagnostics. So here we can do, for example, we have a special pedal tracking. We also do some DM telemetry. Then we have AO-SAT, which is a standard tool we're using for looking at all kinds of metrics in the residual wavefronts. And there is HEAPS, which is a high contrast simulator from the people in Leuven. Some of the results I present today were derived as we are now in the run-up to final design review. With a simplified setup that was not as complete as it is now. So we had, for example, we didn't have the CCS. The AO simulation was a bit shorter. The temporal controller directly controlled the DMs. And mostly we did not have anything that resembled the soft RTC. We could, of course, put some NCPAs or pedal piston, but there was no sophisticated control or feedback of any kind. The evaluation was already there. So a word on wavefront control strategy. So we have a complex approach, it might seem from this graph here. We do a reconstruction in a somewhat unusual way using a virtual zonal deformable mirror that has a free geometry with respect to the pyramid sensor pixels. And we calibrate that by poking the freed actuators one by one, and we do an MMSE regularized inversion of that to derive the command matrix. And then we project the reconstructed wavefront that we derive in that way to a modal set, which is essentially imposed by the CCS, this control system that I already mentioned, which needs to be talked to in modal space. And in that step, we also have the possibility to, for example, derotate or correct any misregistration, this sort of things. Of course, we can then also apply modal gains, filtering, whatnot. Also, again, there is a legacy version. In the beginning, it used to be much more simple. We didn't have the CCS, so we didn't convert actually to modes, at least not in most of the cases. We directly went from this reconstructed wavefront, which I recall was made in a zonal way, to the deformable mirror inference functions commands, which of course also works in the zonal space. So some of the simulations were made in this configuration, some in the more complex, which is available nowadays. So yeah, this is essentially a summary of what has been implemented in Compass. So I already spoke about most of these: custom reconstructor, pedal piston, mask rotation, and so on and so on. On the right side, there are the ones that are very recent or not even fully implemented yet, like this CCS thing and DM rotation and all other kinds of technical, essentially, details. So some simulations. So we have already heard a lot about pedal piston, and actually we are quite happy with our approach. So this custom reconstructor with the MMSE regularized zonal thing is actually capable of coping quite nicely. So on the top right here, this colorful graphics, this is one of the AO standard analysis tool outputs, which gives you a map of the worst pedal piston that occurs in closed loop and the number of RMS pedal piston for each of the fragments or petals, as we call them. And then you have also a plot over time. And then there was an experiment where we deliberately put some pedal piston in the beginning of the loop. You can see this on the top left and how it evolves. Another experiment shown on the bottom is if you suddenly apply something like 700 nanometers in closed loop, and you can see that the system easily does away with such a disturbance. Another thing is looking at NCPAs. So I said that we have feedback from the science camera and we need to update NCPAs from time to time. It's important for the high contrast imaging guys. Typical NCPA amplitude expected is around 110 nanometer these days. And yeah, on the bottom, you can see the response of the system. This is another output of our standard evaluation system. We have a variable parameter on the x-axis, in this case, NCPA amplitude, and on the y-axis, different parameters like strail. The pedal piston is a green curve. So that's RMS pedal piston, RMS tip tilt in red, and the so-called temporal variance contrast, which is a relative contrast measurement that we use to evaluate the impact on high contrast performance. Then, as I said, recently implemented the modal approach to talk to the control system. And we're also pretty happy with that. That was a major step and was not so easy because actually, in every time we do a similar step like this, we notice that pedal piston is actually prone to quickly come back. And it's always a bit of a fiddling and optimization to get rid of it again. But you can see here the performance is almost the same as we had with the original zonal approach. So originally we had on the left are just the strail curves. This is for median conditions on a 10th magnitude star. 123 nanometers RMS, and now switching to this modal approach, we have 129, so something like 40 edit, a little less. And also the pedal piston control is comparable. So if you're on the right-hand side, you have the curves top and bottom. It's slightly worse, and the flare-ups, as Charlotte called them in the beginning, are a little higher in the bottom curve than in the top curve, but in general, it's working nicely and it's still controlling pedal piston really well. Towards the end, let me summarize, or as the title actually promises to also show the performance. So again, we have here the error budget as was determined by the simulations, and actually many more simulations than I just showed you, is in the top third of the table. You can see the summary of the AO residual wavefront error around 123 nanometers in compass simulations. This is in ideal circumstances, yeah, without any further impacting effects. So it's what we call C basic. And then in the bottom 2/3, we're adding all kinds of detrimental effects that we call C full. For example, wind-induced tip tilt. Yeah, I didn't talk about these, but it's a pretty important factor, and of course has a major impact on the residual wavefront error. Static aberrations, static aberrations, residual dispersion, NCPA, and so on. And if we add in all these, we come up with a total wavefront error in these median conditions of 173 nanometers. And so that beeping right now was my 12-minute marker. So I think I should sum up. And so the conclusions are, we have now a fully implemented simulation system that reflects all, not only the major, but actually nearly completely the individual components of the real system as it is foreseen right now. Mostly it's implemented in the compass environment, so for the signal path and the real-time path, and we have an additional soft RTC setup and an evaluation system. The control is based on this zonal VDM MMSE inverted reconstruction, now coupled to a modal control system. Pedaling is well under control. NCPA we have seen and in the orders of magnitude that we expect is also under control. We need to do some final optimizations with switching to modal, and the performance is, I think actually the number is almost the same as the one that Charlotte showed earlier, 123 nanometers. And if we include lots of things that destroy the performance, then we go up to 173. That's it. Thank you.
Okay. Thank you, Marcus. If so there is time for a quick question, if there is any question, let me see on the chat. And Esteban, correct me. I don't see anything for the moment.
Yeah, there's nothing new.
Okay, thank you, Esteban. So in this case, I would go to the next speaker, and possibly Marcus, you can get some question in the question and answer slot, so you may check that one, you know, in a while. And yeah, okay. Thanks. So I think the next speaker for the session. Next speaker for the session here is Jean-François Sauvage, that will present us the performance analysis of the SCAO wavefront sensor for HARMONI. So Jean-François, if you're ready, you can go.
Yeah, can you hear me and see my slides?
Yes, perfect.
Okay. So originally, yes, this work was about oriented toward SCAO. Actually, it's more this petaling effect that I want to present, and it's becoming more and more something more general than simply a HARMONI SCAO problem. So here, so my name is Jean-François Sauvage. I'm working at LAM and Onera. That is grouped today in the Celtic lab. Actually, I'm adding to the very long list of logo of this workshop, the one of the Celtic lab, which is the gathering of LAM and Onera working here in Marseille around instrumentation for ELT and VLT. So in this talk, I want to discuss about petaling effect as we see it in the ELT. So in the first part of the talk, I want to present the petaling effect and position the origin of the problem. And in the second part of the talk, I want to show some results of using super resolution with pyramid to measure the petal modes that we already discussed a lot in the previous talks. So spoiler alert, the super resolution or the enhanced resolution with pyramid is not working to measure the petal mode of the ELT. But still, I present you these results because they are, I think, very interesting for other properties. So I'm beginning with a presentation of the petaling mode in the ELT. So globally speaking, an adaptive optic system is a filter that will take as input some phase aberrations coming mainly from the turbulence, but might be something else, that are cropped by a telescope for which we want to make some measurements in order to compensate for them and have a very nice PSF at the end on which we can compute any quality criterion. So in the ideal case, the phase is composed only of turbulence and the telescope has no spiders. This is really ideal. In this case, any wavefront sensor gradient-like the modulated pyramid or the Shack-Hartmann are able to measure the aberrations, and we can compensate for them and have a very nice PSF at the end of the level that we want. As soon as we add some large spiders to the telescope, so like the one we have on ELT, 50 centimeters, then we have all seen that spurious mode appearing. The wavefront sensor is not able anymore to measure the piston mode for each of the petal. Then when controlling the loop, there is this kind of residual that appear at the end that is completely degrading the quality of the PSF. So we call that the island effect at some point, or the petaling mode. Well, the wavefront sensor don't see them, then the controller is not able to measure, to correct for them. The solution that we propose with HARMONI, SCAO, and that is used also in some other studies, is to slave the actuators or to pair the actuators side by side along the spiders. So this is a control solution that works almost okay. I say almost because we still have some residual that degrade a little bit the performance, but we can deal with them. But most of all, I say almost okay because as soon as we add to the turbulence some other perturbation that I call here delta phi to be general, but that can be made of discontinuity modes like the nuclear modes here that I'm showing. If this kind of mode appears on top of the turbulence, then this solution that we have before, which was done on purpose not to control this mode, is unable at all to do anything to fight this additional perturbation. So definitely we need to have some way to measure these modes and to sense these discontinuity modes delta. Oops. Sorry. So on this perturbation, there is a very fundamental question on the fact if they are static or dynamic. If these modes are purely static, then we know some solutions to measure them, which are not the pyramid wavefront sensor, but by instance in HARMONI, there is a high contrast mode that embeds a Zernick phase mask, a Zelda mask, that is able to measure this kind of modes. So if these modes are static, then we can make a quick calibration with a high contrast mode in HARMONI, and then compensate for them, and then spend the night observing with a nicely compensated phase. If this mode becomes dynamic, and of course it will be dynamic, meaning it's evolving faster than the exposure time of the science, then it's becoming an AO wavefront sensor issue. We need to measure and to control them during the observation. That might need eventually to use a dedicated wavefront sensor, we call about petalometer at this point. So what could be the possible sources of this aberration? On the first one I already talked about is the AO-generated petal modes that we call islands at some point that are actually introduced by the loop just by the wavefront sensor. The usual wavefront sensor are unable to sense it. So this is typically a dynamic petal that we can prevent by pairing the actuators, although this is not very sufficient. Another source of them is in the ELT, the presence of a segmented M4 deformable mirror that is actually not completely able to phase each of the 6 petals of its surface, due to the fact that the reference body that's supposed to make a uniform mechanical reference for each of these 6 petals is not completely referenced and is not really able to phase everything. So this will translate into an unseen static petal perturbation. Another source is the famous low wind effect. That's an optothermomechanical effect introduced around the spiders of the telescopes that has been first seen on the VLT. This is a pupil of the VLT actually. That's translating into a dynamic and unknown discontinuous perturbation. So today, what we say, it's composed of petal and tip and tilt for each of the segments here. This is a rough approximation, but it's very large and evolving with time. So this is really a problematic term. Another origin of discontinuous mode might be also coming from the strategy of ensuring the continuity of the primary mirror of the ELT. So any aberration on the segments of the primary mirror will turn into discontinuity. That will be the strategy is to minimize this discontinuity by moving all the segments together. And some of the segment level aberration might introduce this kind of nuclear mode, by instance, that will be perfectly unseen by our wavefront sensor. So there are many origins for this delta field discontinuous mode. For each of them, it's very difficult to put numbers, either in amplitude, in nanometers or microns, or in temporal behavior as well. Is it evolving at the millisecond scale or second or minute? It's difficult to put numbers on this, at least today. So there is many reasons why we should look for ways to measure these modes. So as Charlotte has just said, in our baseline for HARMONI SCAO, we have made everything so that our system doesn't introduce any of this nuclear mode, so which was perfect until we say then you have some inputs and you need to measure and to compensate for them. So these modes are completely untouched by the SCAO system, so they are directly degrading the performance. So Charlotte just shows that if you talk before. So this mode will directly degrade the performance of the HARMONI SCAO mode. So if I consider a low wind effect on ELT composed on piston tip and tilt on the segments, and I look at how the Strel is degraded, of course, it's falling very, very, very fast after a few tenths of nanometer, 100 nanometer at H or J or K band. This is typically the amplitude of low wind effect seen on sphere on the VLT before recoating the spider. Okay, after recoating the spider, the performance was increased. Actually, so the effect was decreased, but and the performance was increased again. We have no idea on the ELT where will be these two spots here of performance, rather in large amplitudes and very small one. But this is really undergoing ongoing studies. So there is a real interest to try to put to have some wavefront sensor that are able to measure these modes. So just a quick map of some of the selection of the talks in this workshop that are dealing with these issues. You have already seen the Charlotte's talk about what is the impact of this mode in the SCAO performance. There was also the Carlos talk about using super resolution. I will also pursue on this notion just after. There is another way, still using what we call the first stage solution. That would mean using the first stage AO wavefront sensor to measure this mode and to bring some correction. It is to change the wavelengths. I just show Marcus Feld, go to K-band wavefront sensing, and then you get some natural coherence of the wavefront between each part of the spider, and your wavefront sensor becomes sensitive to this mode, at least more sensitive. So there is also what we call second stage solution. So after the first stage, you had a dedicated wavefront sensor that could be based on spatial filtering, non-modulated pyramid, or Zernick phase mask. You can see the talk by Nicolas Levrault later tomorrow, studying this solution. So I want to keep on going here with using super resolution of the pyramid. Why do we want to use super resolution? If we are facing a discontinuity, it means that the phase is evolving very fast with respect to the position in the pupil. So increasing the resolution is a way to try to follow the phase modification. So we want to increase this spatial resolution in the pupil plane. So there are different ways to improve this resolution. The first one, it's easy, is with your detector, just increase the number of pixels in order to make some pupil measurements. So that would be a high resolution pyramid wavefront sensor. Another way, which is then just keeping the number of pixels in the pupil, but using multiple pyramid wavefront sensor, each of them shifted one with respect to another. This is what Carlos introduced as the super resolution. So there would be, in this case, 4 pyramid wavefront sensor, with each of them which is its detector, and we shift globally the 4 pupil image on each of the detector to bring this super resolution. Another way to think about this is to use a single pyramid wavefront sensor and to use the fact that we have 4 pupil image and we just want to shift them with respect to the pixel grid, trying to see if we can benefit from a kind of super resolution effect that we call enhanced resolution, just by shifting the pupil image. So we can shift globally each of the pupil with respect to the pixel, or we can shift them differentially. This is already what Charlotte showed in our talk about SCAO, or we can shift them in different ways. So what I did here is to actually compare all of these wavefront sensor here, and I'm comparing them by plotting by doing a calibration of one of these wavefront sensor. I'm using a toy model of a 10 by 10 pixel pyramid wavefront sensor, and I'm using a 20 by 20 actuator deformable mirror. So usually we don't have enough pixels to measure all of these actuators here. And I'm doing a calibration and I'm plotting the eigenvalue of this interaction matrix with respect to all the modes available on the deformable mirror. So usually we have 2 regimes, the well-seen modes that are usually measured by the wavefront sensor and then controlled, and all the bad modes, which are the high order modes that we cannot see with the low resolution deformable mirror. So these are all the eigenvalues that I plot for each of these for each of these wavefront sensor. So the 4 bottom lines here, 2 of them are superimposed, are actually 10 by 10 pyramid wavefront sensor, just differing by global shift of the pupil, either in X or in Y, or in X and Y combination. We find here the well-known eigenvalue plot where all of these wavefront sensors are decreasing sensitivity to the eigenmodes until a moment where we don't see anything anymore, and all the higher order modes are unseen by this wavefront sensor. Now, if I'm putting some differential shift between the 4 images of the pupil, then I'm gaining a lot in sensitivity for all the higher order modes here. So depending on which kind of shift, if I'm keeping one of the pupils fixed and moving the other ones, or moving each of the pupils, there might be some slight difference between them. But globally speaking, we're improving the sensitivity on all the higher order modes here and keeping a reasonable sensitivity on the low order ones. Yeah. So this is a very interesting regime where we gain in sensitivity on higher order modes, keeping a small number of pixels. Here I still have only...
Jean-François, sorry, you have 2 minutes nominally.
Okay, excellent.
Sorry.
So the 2 last curves are the real super resolution pyramid here, which is this blue one. So we see all of the intermediate results here that are enhanced resolution are just below. And the top curve here, the red one, is just increasing the number of pixels in the pyramid. So here you gain in sensitivity on all the modes here. So, okay, we gain in sensitivity for higher order modes, but these higher order modes are actually not petal modes. If we look at the gain in sensitivity for these petal modes, or just putting some real petal modes in the system and calibrating them and seeing what is the gain in sensitivity, it's not at all in the same order of magnitude. We gain a little bit ×3, but this is not what we are looking for. We want really to gain a lot of sensitivity, and this is not the case. So what I just showed is working on higher order mode, and this is quite interesting actually, to drive a higher order DM with, let's say, a a mid-order wavefront sensor. This is something quite interesting for HCAO domain, by instance, but it's not working for petaling. So just as a conclusion, so reminding the petal is an effect created by the presence of large spiders that makes the wavefront sensor insensitive to some phase steps, so that can have different origins. What I tested here is the super resolution case. It's actually, from what I think, not working for petaling, but that's a very interesting solution for HCAO wavefront sensor. As it's a workshop, I'm just throwing an idea of something we didn't explore, I think, as a petalometer, is to use the pupil densification. So this is a concept that's coming from the hyper telescope of Antoine Laberry. He was using different parts of the pupil and was optically recombining them side by side before making a high resolution image in a focal plane. Without going to the focal plane, we could use that actually to shift parts of the pupil optically before entering into the pyramid, and then forming a pyramid image with actually removing all the shadow parts coming from the spider. So this is really a completely open idea. I have no evidence of this is working or not. I'm just throwing the idea here, and if you have any feedback, these are welcome. So this is all for me. Tell me if you have any questions.
Thank you, Jean-François. Thanks for the talk. I think we are running a bit late here. Do you have a question from Andreas Obereder that basically saying if the behavior of the eigenvalues is that we see in your simulation could be changed by changing the modal base? If you have a very, very quick answer for him.
Yes, okay, there is definitely some impact on that. Actually, we also tested that with different bases. This way of representing the thing is the most visual to see the improve of sensitivity on these higher order modes. We can discuss that more offline if you want.
Okay, thank you, Jean-François. So thanks for the talk. And then I think we go with the last talk of the session that is given by Vincent AO, and the title here, Interferometric Wavefront Sensing at Subaru, SCExAO, fiber and pupil remapping spectroscopy and non-redundant masking. Vincent, if you're ready, you can go.
Yeah, thank you, Simone. Hello, everyone. Happy to be there this morning. So I'm going to be speaking about some interferometric instruments we have at on the SCExAO platform at Subaru. So this work is being led by a lot of people at a lot of different institutions. So just wanted to give a big shout out to all of those guys before starting. So let me give a brief recap on the current state of exoplanet search. We have lots of exoplanets that have been found with indirect detection methods transiting in radial velocity, and very few planets at this stage that have been found using direct imaging, only about 20. And we are restricted for now on 8-meter class telescopes to only the bigger and most separated planets from their host stars. Here are very famous images from 51 Area B and HR 8799, which are record cases of direct imaging detections. And so, of course, the rise of ELTs is going to improve the resolution and bring us into this pink zone where we have a high number of expected Jupiter-like planets. This corresponds to 1 to 5 AUs at 140 parsecs. And it will help when we can image these exoplanets, it will help us answer key questions about exoplanetary science. And so the technical requirements there, and the question that we want to answer is, can we get into that pink zone a little bit with 8 meters telescope before we have the ELTs? And for that, we need high contrast and high resolution. And to increase our resolution versus the typical 2-3 lambda over D limit of coronagraphs, one solution is to use single aperture interferometry, which theoretically allows resolution down to half a lambda over the longest baseline of the interferometer. So single aperture interferometry is when we introduce a sparse mask in the aperture of the single telescope. One technique to do this is non-redundant masking, where the baseline between every single hole, this is a 9-hole mask overlaid with the Subaru telescope pupil. And each baseline is unique. And then we form the far field propagated interferograms from which, by Fourier transforming them, we can read the fringes on every single non-redundant baseline. The problem with non-redundancy is that it puts a very strong restriction on the coverage in the pupil plane. Although it's a very ancient technique and has been routinely used for a very long time. So the alternative to this is redundant masking with aperture remapping. So we are going to put mask holes in the pupil plane again, except now we have repeated baselines, which if we were to use direct propagation would do overlapping fringes and with a very reduced contrast and basically be unreadable. So every single subaperture, every single hole in the pupil plane is injected into a single mode fiber or waveguide, but the E field is conserved. And then we can put all those fiber heads at the exit into another pupil plane into a now non-redundant configuration and image the fringes. And so the remapping allows disambiguation of the originally redundant baselines. And this is exactly what the first instrument that is installed at on the SCExAO platform at Subaru does. So there are 2 sets of 9 fibers. We use one of them at each time. And this allows a resolution in at 700 nanometers. The instrument covers from 650 to 800 roughly of 10 milliarc seconds with a spectral resolution of 300. And so as you can see in the middle, we have this array of single mode fibers that are rearranged into a nonlinear one-dimensional array, on top of which we had an anamorphic lens and a prism, which allows to have spectral dispersion on one axis and the fringes on the other. So how are those instruments, interferometers, used for science? I apologize for the mathematics on this slide, skim over it very quickly. The important quantity is when we Fourier transform a set of fringes over a baseline, we obtain the complex coherence for this baseline, which contains the yellow term, which is the astronomical source visibility. So essentially it's an angular Fourier transform over the sky. And then a technical term, the amplitude that got into the 2 interfering subaperture and the OPD on the baseline. So when doing science, actually the baselines are processed 3 by 3 in triangles. And the goal of that is to actually have the phase terms cancel out. And this is exactly why sparse aperture masking was introduced, so that when doing the scientific data reduction, we don't have to care about turbulence or instrumental optical path differences. Therefore, the closure phase, the triangle subtractions are self-calibrated and allowed to retrieve whatever asymmetries are hidden in the visibility of the object. And then we use forward modeling, either modeling disk, modeling star binaries, or with variable contrast, and do forward modeling to retrieve the asymmetry. This on the right is one key scientific result that was obtained with first of the spectroscopy binary alpha equilius. So on the left is a likelihood map of where the second component should be versus the central star. And on the right, the ratio of spectra around H alpha, with a separation that was measured at 0.6 lambda over d while achieving below the theoretical resolution of the whole aperture. This is another result that's in preparation, imaging capilla with a 46 milliarc second separation, just a couple lambda over d's, as you can see with the image in the visible. And so the results with orbit fitting, we have X-ray box in 2021, and this should be out next year, the characterization of the capilla. So of course, we've been talking about science so far, and the recurrent problem is for these interferometers, the wavefront stability. And so how can we turn first into a wavefront sensor? So back to the data processing, of course, for wavefront sensing, we're interested in the technical term that science reduction has been discarding, but the information is right here. And so we're going to use exactly this term for IWFS. interferometric wavefront sensing. And so from the 9 holes in the pupil plane, we have 28 pairwise baselines. But when we take the argument of the measured visibility, we realize that there are a lot of phase wraps. So this figure, so the 28 inserts are the OPD over each baseline, and the blue lines for each baseline that's plus minus half a wavelength. And so we have this very numerous wraps over the spectral capability of the instrument. And the fact that we have lots of wraps is actually because we have very large static OPDs between the various subaperture that actually come from the single mode fibers that are from to the reimaging pupil plane. Simone, could you confirm you're still hearing me, because my headset just said it was dying and there was no battery.
Yes, there was a glitch, but I hear you. Yeah.
Perfect, thank you. And so to compensate those very large OPDs that actually between individual pairs of fibers can go up to 100 microns, and on top of that are vibrating with and changing wildly with any sort of vibration of the structure holding the fibers, we added optical delay lines to compensate for that. So those are electrically controlled with a little mirror inside the box that allows us to vary the path lengths for each individual fibers and then match them. So here you can see this little GIF as we're sweeping over the path difference in the OPD box and trying to find the central fringe. Unfortunately, this has got trickier than expected, because by introducing the optical delay line, we replaced a fiber optical path difference by an air optical path difference. And now we have a very strong amount of chromatic dispersion that you may see in the curviness of those fringes. And so to try and calibrate all of that, we added a metrology laser source, which is this Torlabs box, which has four laser diodes of your choice, which are recoupled together into a single fiber. And now this is what we see on the instrument. We have those 4 lines that come from the metrology source internal to the instrument, and then the astronomical signal that is in the middle. And so the metrology lasers only really see the instrumental fluctuations, and the laser has been put really close to the fiber heads. So it really only sees the fibers shaking. And then this should allow us in post-processing to isolate the component due to fiber shake and the component due to atmospheric turbulence. So we hope to have some more serious analysis next time we talk about this. So I'm doing this talk backwards, and now I'm going to say why interferometric wavefront sensing more generally beyond FIRST is extremely interesting. With a spectrally dispersed interferometer just as FIRST, we have polychromatic wavefront sensing. FIRST has 300 resolution, but we don't need nearly that much for chromatic characterization of the instrument or the atmosphere. But it's an interesting fact that chromatic aberration is going to be the next big budget once we get after phase and scintillation, and for high contrast, we will always need to go deeper. The interferometric part of the sensor gives a theoretical excellent sensitivity because every single photon really directly contributes to wavefront sensing. There is no photon loss, photon that's not used for sensing. And this is going to be amazing for co-phasing problems and pedaling. Yes, you knew this talk was going to be about pedaling at some point. And we have a very high capture range if we combine multiple wavelengths, because then we can measure the group delay and extend the capture range well beyond 1 wavelength. And finally, in the case of FIRST, it's extremely interesting that the wavefront sensing is directly inside the scientific instrument. And since NCPs and quasi-static speckles are one of the most significant contrast limiters in high contrast imaging, having a direct wavefront sensing measurement at the science plane will be most interesting. So hopefully we can have on-SCAO wavefront sensing with its metrology source and everything sometime next year. And so going around the hurdles one by one and hopefully getting there. So while we're fixing that, we went back and I took the side project of doing direct far field interferometry and using this possibly as an interferometric wavefront sensor. And with another goal, which now is straight into pedaling, to see if this technique could be used to supplement the pyramid wavefront sensor, where it's a little bit struggling. And so in particular with
Vincent, sorry to interrupt you, but you have nominally 2 minutes.
I'll be quick, thank you. So those are interferograms that were acquired on the laser source of the SCExAO bench. So this is using a CRED 2 and upgrade to a CRED 1 is coming up. So in our 3 main observing bands, and we can read those extremely fast speed thanks to those fast cameras, and we have just about the right sampling to do this. So that's our sample, and so that's how I set up the non-redundant mask, the sparse aperture wavefront sensor. The processing is fairly simple. We take the Fourier transform in the interferograms, which gives us this correlation map where every single blob corresponds to one baseline, from which we deduce the pixels that are relevant to our analysis for every single spectral configuration. And so if we look at the phase, the argument of one interferogram through this label mask, every single domain is the direct readout of the wavefront phase over each baseline of the mask, from which we can start pulling out the AO toolbox that we know very well and start doing also RF characterization from this pre-processed baseline signals. So here are linearity curves for tip tilt and a low wind effect pedaling basis. And we were happy, and so every single curve is the phase in radians over one of the 28 baselines of the 9-hole mask. And so we're happy to see that the capture range before any wraps occurs was consistently when one of the baseline reaches plus or minus pi a phase, and that the linearity besides distortion effects at the edge of the pupil was excellent compared to other things we experimented with. So this put the sparse aperture wavefront sensor as a very strong candidate for pedalometry, which is a problem that is absolutely recurring even on SCExAO. So on 8-meter telescopes with spiders, they're not all that big. And so these are some on-SCAO results that were taken this summer. There's a little bit of backstory to HCAT, but essentially we were applying those differential piston maps on the internal deformable mirror in SCExAO, and then closing the loop with the sparse aperture wavefront sensor to try and correct them. And so for these 3 of the 4 cases with the temporal curves, so each curve is tracking the value of the piston, we see we have convergence, but of course, life wasn't always that good. And you can see on the force case at the bottom right that this one was gloriously diverging. So there is still work to do, and this will pave way for more elaborate designs, such as FIRST. And this is an excellent tool to prototype actually multi-AO loop algorithms that we will need when we have several wavefront sensors cooperating together without being synchronized whatsoever. And so this is excellent for prototyping RTC work. And so here we are. So FIRST is on track for its new version as well, for the array of single mode fibers. Well, the far field combination for the fringes will be replaced by a photonic chip, and so we'll have the interferences happening directly on a crystal, a photonic chip crystal. And we'll have wavefront sensing and fringe tracking hopefully next year, and in parallel, the technical prototyping with the sparse aperture wavefront sensor. And thank you very much for your attention.